Okay, this is the video for the third day of fundamental identities. We've been working with the identities, the quotient, the reciprocal, the Pythagorean, and there are some other techniques for verifying an identity. Here are some tips. When you're verifying an identity, you're going to work with one side only, the more complicated side usually. We've done this before. We're going to look for ways to factor, add fractions, square a binomial, or get a common denominator, and that's what we're going over in this video. We're going to look for ways to substitute one of the fundamental identities, and if all else fails, convert everything to sines and cosines and go back to step number one. There's some ideas in your book, but bottom line, try something. Keep trying. There have been identities that I have gotten to the bottom of the page and realized I didn't have it and had to start all over. Okay? That's typical. It's a puzzle. Don't get discouraged. Okay, the first technique is to convert everything to sine and cosine and see if something cancels. Okay, so first of all, cotangent, right, is cosine over sine. Secant is 1 over cosine. You can see right now the cosines are going to cancel. The cosecant is 1 over sine. And then I have just sine x over 1. And so I'm looking for forms of 1. The cosine, cosine, the sine, and the sine, forms of 1. I'm left with 1 over sine, which is, right, cosecant. So this whole thing is cosecant x. In other words, this side can be made to look like this side. Okay, number 2 is substitute an identity for one or more values. We have seen this one before where we had the Pythagorean identity for this was sine squared x plus cosine squared x equals 1. And remember that sine squared x would equal 1 minus cosine squared x. So in other words, I can substitute sine squared x for 1 minus cosine squared x. So I will do that. Sine squared x. Cosecant is 1 over sine. Right? I can cancel one of those and I'm just left with sine x. So this expression right here is equal to sine x. In other words, again, I can make this side, the left side, the more complicated side, look like sine x. And that's what I want it to be. So right now I'm just simplifying an expression. I'm not verifying an identity, but I'm simplifying. Okay, this mess over here is what I tried to type out onto here, and it did not come out the way I wanted it to. So I'm going to rewrite this. I hope you don't mind. This is the cosine of negative x times the sine of pi over 2 minus x, and then plus sine squared x. This is what I want it to say. I don't know what it says up there, but this is what I want it to say. Okay, so what I want you to see is that this is from the first video that we looked at. This is the even or odd function. And we remember that cosine is even here. This is the cofunction. This is a cofunction. So it says that the sine of the other angle is equal to the cosine of x, right? And then this is just sine squared x. All right, so we know that this is even. Since cosine is even, the cosine of the negative angle is just cosine of x. All right, we know from the cofunction that the sine of 90 pi over 2, or 90 minus x, the other angle, is also cosine x, and then plus sine squared x. Well, cosine times cosine is cosine squared x. Cosine squared x plus sine squared x is, you guessed it, 1. So this whole mess here was equal to 1. That's equal to 1. And that's what we're doing here. If we were verifying the identity, it would actually say 1 equals this mess right here. And so what we would be trying to find is simplifying this down so that both sides look like each other. Another technique is to factor. And over here what we're looking at on this side is we're looking for a common factor. You can see this is a term, a minus sign, and another term. So one thing that we're going to do is we're going to factor out a tangent squared from both sides, and then I have 1 minus secant squared x. Now, there is, if you see a 1 and something squared, it's a Pythagorean identity. And one of the Pythagorean identities is 1 plus tangent squared x is equal to secant squared x. Okay, so that sort of looks like what we have up here, but not quite. So I would, if I did this, if I said tangent squared x equals secant squared x minus 1, in other words, I move the 1 to the other side, then I'm sort of close, right? That's not 1 minus secant, it's secant minus 1. So what if I multiply through by negative 1? Then I'm closer. So I have, up here, I have tangent squared x times negative tangent squared x. So this would be negative tangent to the fourth x. And that would simplify the equation. All right, here over on this other side, we see something that looks a little bit like a quadratic, and we can factor it the way we would a quadratic, even though it's to the fourth power. So I'm going to write it like we would be factoring, and secant to the fourth x would be secant squared x and secant squared x, 1 and 1. It's all positive, so this is positive, and so I have both of these. Now, I can look down here and see secant squared x plus 1. And that's really all you can do with that one. If you'll look down here, there is no way with this, to do any more substituting here. So a better problem would be if I had tangent to the fourth x plus 2 tangent squared x plus 1. I mean, I can factor that the same way, right? It is a perfect square with tangent squared x plus 1. Now, if I look at this, tangent squared x plus 1 is just secant squared x. So this would be secant squared x squared, and that would be secant to the fourth power, secant to the fourth power x. And so that would be a better example, I think, of factoring than the other one, because you could actually substitute something for it. This, there's nothing you can substitute for that. I mean, you could put tangents in there, but I don't even know why you'd do that. So moving on. Okay, here's another example of using the difference of two squares to factor something to simplify. And remember, the goal here is to simplify. So I'm going to go ahead and factor this because it does look like a quadratic. I have sine squared x and sine squared x. Cosine to the fourth is cosine squared x, cosine squared x. There's a minus sign, so there'll be minus and plus. Now, one of these can be substituted for. It's a Pythagorean identity. If I have sine squared x plus cosine squared x equals 1, right? So I know that I can substitute a 1 for this. Is there any way to substitute, to add or subtract one of these to make it look like sine x minus cosine squared? Sine squared, and you can't. So this turns to 1. And so my simplified answer is going to be just sine squared x minus cosine squared x. Actually, you could, if you needed to change all of that to sine, you could say that cosine squared x was equal to 1 minus sine squared x, and you could substitute for it. You could do the same thing for sine squared x. You could substitute a 1 minus cosine squared x. It depends on what you need here, but you cannot call it 1 because of that minus sign. You could also factor it, could you not? You would say sine x plus cosine x and sine x minus cosine x. but there's nothing to substitute for either of those, so you might not need to do it. So at this point, you would update it depending on what you needed. And so I probably would just leave it like that. It's kind of interesting that the simplification of sine to the fourth x minus cosine to the fourth x is sine squared x minus cosine squared x. That's kind of an interesting thing. And then they both factor the difference of two squares, which is kind of interesting. Another helpful technique is to find a common denominator, just like you would for fractions. You can see here you have 1 over cosine squared theta minus 1. So the common denominator for this equation would be cosine squared theta. All right, so 1 can be written as cosine squared theta over cosine squared theta. If I combine the denominators, I would have 1 minus cosine squared theta over cosine squared theta. And you're seeing that anytime you have a 1 and a cosine or a sine squared, it's a Pythagorean identity. This one happens to be sine squared theta plus cosine squared theta equals 1. So sine squared theta is 1 minus cosine squared theta. So where I find this, I can substitute sine squared. So this is going to be sine squared theta over cosine squared theta, which is what? It is tangent squared theta. So those two things are equal. So what you're finding is a common denominator here, and then combining the fractions. And then here is the Pythagorean identity that you used. Okay, the last technique that we're going to use is a very specific type of problem, and it's called trig substitution. So what you see is you see the square root of 9 minus x squared. It's kind of like u substitution. You've simplified it by putting a variable in here, but what x truly is 3 cosine theta. So using trig substitution, what you would do is you would rewrite this part, 9 minus, and leave some room. What is x? X is 3 cosine theta. So I'm going to substitute that value in there. 3 cosine theta, and be careful when you square it. The next one would be 9 minus, 3 squared is 9, cosine squared theta. All right, you can notice that both terms under the radical have a 9 in it, so we're going to factor that out. And that's going to be 1 minus cosine squared theta. We remember from sine squared theta is 1 minus cosine squared theta. So I can substitute, and I have 9 sine squared theta. If I take the square root, I have 3 sine theta, and that is the answer. So we're using a substitution then to find the actual answer. Here are the two problems that I want you to work in your composition notebook. Number 1 is a substitution problem. Number 2 is both a substitution in a different way, substituting an identity and also factoring. So I want you to change it to all cotangent and then factor. Have these ready to go in your composition notebook, and I will see you in class tomorrow.